talk is mainly joint work at various stages with my collaborators, Chang, Yang, and Leung. Okay, so now my talk will be divided into several sections. The second section is about a conjecture for two positive maps in from M3x3 matrix algebras, and the third section will be describing a decomposition for K positive maps, and in the last section, then I would like to mention some connections with quantum information theory. Okay, so I'm following the standard notations for matrices. Then we are dealing with complex value matrices. So a positive semi-definite matrix or simply positive matrix is denoted by A bigger than or equal to 0. And of course, Mn plus denotes the collection of all positive matrices. And then the L from Mn into Mn is the space of all linear maps from Mn into Mn. Now a matrix, positive matrix in the Mn tends to Mn, and quite often I will be identified that with M by M block matrices with entries in the Mn. Such a matrix is said to be separable. Then if A is in the tensor the cone, Mn plus tensor Mn plus. And otherwise, it is said to be entangled. Okay. Now, of course, we know that this is properly contained in the biggest positive semi-definite matrices, and most of the time, then we don't have equality unless that means in the context of matrix algebras, then we have unless M is or N is 1, right? Yeah. So and then a matrix is said to be PPT if both A and this so-called partial transpose basically is the transpose in the blockwise manner. It's also the positive. Okay. And then now, of course, I denote identity map on Mn, Mk by ID of K, and likewise the transpose map by T sub K. A linear map is said to be positive if it sends positive matrices to positive matrices. And then it's said to be K positive if the implication map identity tensor phi, and the map is as a map from a matrix algebra Mk by M into itself, and is said to be positive in the previous manner, right? Now, of course, for me, quite often I will consider the identification in the blockwise manner. So that means it sends the K by K matrix with Aij at the Ij position to phi of Aij to the Ij position. Whereas then it's said to be K co-positive if then the tensor product of the transpose map with the map phi itself is positive. Okay. Now then it means that when I consider the block matrix Aij, it will be mapped to phi of Aji. And then such a map phi is said to be completely positive. It is K positive for every K. And then it's completely co-positive if there's K co-positive for every K. And a map is said to be decomposable if it is the sum of a completely positive map and a completely co-positive map. Okay, so there's a very simple characterization of completely positive maps on matrix algebra by Mandarin Choi. So now if we use the standard notation, EIJ is the canonical matrix unit in the Mn. That means, of course, it is 1 at the IJ position and 0 elsewhere, right? EIJ. Then we form the so-called Choi matrix. And basically, in the block-wise approach, then it is just an M by N matrix whose IJ entry is phi of phi at EIJ. Then Choi proved this result that a map is completely positive if and only if then the corresponding Choi matrix is positive. So it is a very simple characterization of completely positive maps on matrix algebras. Okay, so now, of course, even for low-dimensional matrix algebras, then the structure of positive maps is very complicated and is not fully understood. So now in the 1992, Choi, Kai, and Lee then proposed some positive maps on M3, which are generalizations of a special map considered by Choi much earlier. And for the 3 parameters, A, B, and C, then they defined a family of maps in this manner. Phi at A, B, C, a map from M3 into M3 in this manner. Now, the original choice map then takes the special numbers A equals 1, B equals 0, and C equals 1. And it has very interesting property. It's indecomposable and it's extremely positive map. Now, indeed, this is the first example of a positive map that is indecomposable on the matrix algebras. So now these 3 authors consider this generalization, and then they determine conditions on the A, B, and C such that these special maps are positive, 2 co-positive, etc. Okay, and then for this special class of maps, then it turns out that they prove this whenever the map is 2 positive or 2 co-positive, then automatically then it is decomposable. And of course, a natural question then is to consider whether this result is still true for any general 2 positive maps from M3 to M3. So, and this is the first conjecture we consider in this talk. Okay, so that means we ask whether every 2 positive or correspondingly 2 co-positive maps from M3 to M3 is decomposable. Now it turns out that this conjecture is related to some information or some consideration in quantum information theory. Okay. So now for this purpose, I will just be very brief in my description. If I have time later on, I'll return to that. Okay. So now you recall that say Mn tensor Mn plus tensor Mn plus, then it's sitting in the biggest Mn tensor Mn, the whole positive cone, right? Then we know that those maps in this smallest cone is called separable. So it means that we have a lot of things in between. Okay, so then one would like to have a better description of the or have a better understanding of the gap in between. So then the Taha and Rebecca and about 20 years ago introduced this concept called Schmidt number, okay, which will have a better description of those things in between, okay. Okay, so now I don't want to go into the detail here because of lack of time. Then it turns out that say some other authors then have this consideration. Now, when they consider the bipartite quantum system, C M tensor Cn. So of course, correspondingly, as the matrix or the states, then it is Mn tensor Mn. Now, in general, then for some special situations, they have proven that they have proven for some special cases and some conditions here, right? And those as Schmidt numbered 2. And then they conjecture that in the special case, m equals n equals 2, and all the entangled states, which means that they are not separable states, must have Schmidt number 2. Okay. It turns out that this conjecture 2 and the previous conjecture 1 are equivalent in the following manner. So basically, then we have a bilinear pairing between the tensor space Mn tensor Mn with linear maps from Mn into Mn, okay, under this bilinear pairing, okay. So, and then from here, then one can describe the relationship between the Mn tensor N and linear maps from Mn into Mn. So there are some sort of descriptions here. So let me, because of lack of time, let me skip the detailed explanation. Then it turns out that, and say Pk is the collection of k positive maps. Then we have this bilinear pairing. So we have the biggest cone positive maps and so on, and k positive maps and completely positive maps. Whereas on the other side, right, then it is say the separable states or separable cones and so on, right? So the last one then is Mn tensor Mn plus, and actually this is the cone corresponding to those Schmidt number, then is less than or equal to k. Okay, so therefore then we have this bilinear pairing, and then in the special case when m equals n equals 3, then it means then we have this situation. So the problem then is to sort of determine whether for the level of linear positive maps, then whether the decomposable maps then sits in here, okay, or in other words, then whether all 2 positive maps are decomposable. Whereas at the level of tensor space M3 tensor M3, then this is the separable ones, right? V1, and then this is Schmidt number say less than or equal to 2. And we are asking then whether those so-called PPT states then will sit inside here, or in other words, then whether we have all the PPT matrices will or states, right, will have Schmidt number less than or equal to 2. Okay. Okay. So by this bilinear pairing, then the conjecture 1 and conjecture 2 are equivalent. Okay. So I still have 5 minutes. Is it? Okay, so I have to be a bit quicker. So it turns out that then it's related to a previous result of Masinic, which shows that any non-zero two positive maps has a decomposition. So we can split phi into two parts, a completely positive part and a positive part. So every two positive maps, then we have this decomposition, okay, on the matrix algebras. So now then we'll be presenting a slightly stronger version. Now here we make use of the block matrix approach. So basically, I think we have this notion about so-called lifting. So I think it is a bit complicated in the explicit formulation. So let me just go to the next page. Now, basically, say we have originally a map from Mn into Mn, right? Then we want to blow it up, okay? So then suppose we have a bigger dimensional space. Then we want to just lift it to phi tilde. And we have the same image for the actions, right? So of course, in abstract manner, then you may consider the appropriate projection from the bigger matrix space into the smaller one, right? But in terms of the concrete explicit expression, then it means that we are just adding zeros to the Choi matrix, to the new Choi matrix. Okay, so roughly that is the idea. Okay, okay. So now it turns out that in this case, then now of course we have preservation of positivity, K positivity in this process. Okay, like decomposition, the stability is also preserved under this so-called lifting situation. Okay, so it turns out that then if we start with a K positive map bigger than or equal to 2, then we have a decomposition of phi, where we can split it into a completely positive map and another map, which is basically living in one dimension lower, and it is then K minus 1 positive, right? So that is the sort of main result for this purpose. Okay. Now the whole point is that then this part here then is has one positivity less, right? But it also lives in a dimension that is smaller. Okay, and likewise we have a corresponding result for co-positivity. Okay, so now of course you can iterate this, right? If you iterate this, then starting with a K positive map, then you can split this as the sum of at least K minus 1 completely positive down to a positive map. Okay, but the dimension of that effectively will be K minus 1 dimensional down. Okay. Okay, so now by making use of this result, then we can prove that in the for maps on the matrix algebra M3, then every two positive map or correspondingly two co-positive maps then must be decomposable. Okay. So now the idea is actually very simple. So now because of the previous result where we split this two positive maps into a completely positive one, and this is positive, right? And it's the lifting of a positive map. But this is staying one dimensional lower. So basically, the unlifted one, maybe you consider, this is the lifting of that. Then we'll stay in the M2. Okay? But then there's one very important result by Voronowicz.
that every positive map from M2 into M3 is decomposable. So as a result, then this K derived map is also decomposable. So as a result, then it's a completely positive one map plus a decomposable one. So therefore, the sum is still decomposable, right? Okay, so then now of course there are some related questions, and whether then every 3 positive map is from M4 to M4 is decomposable, right? Just now we have proved that every 2 positive map from M3 into M3 is decomposable. So we may consider the next step, okay? And more generally, then whether every n-1 positive map from Mn into Mn is decomposable. Apparently, so far I don't know the answer. Okay, so now finally, let me just mention a connection with quantum information theory. Now, a linear map is said to be a PPT if it is both completely positive and completely co-positive. Okay, and correspondingly, it means that the Choi matrix then is a PPT. So this matrix is positive, and this sort of block-wise transpose matrix is positive. And then the map is said to be separable. And if the corresponding Choi matrix is separable, or the Schmidt number is 1, then Christian proposed this interesting conjecture. And if we start with a PPT map, then the composition of phi of itself then is separable. Okay. Now it turns out that there are quite a number of important partial answers to this conjecture, namely by the Professor Paulson's group. Okay, so they have proven a lot of very nice results. So now if unital and trace preserving PPT map phi, then it's not right away that the composition of phi of itself is separable, but rather then when you consider the sequence of its rays, then the limiting points are separable. Okay, and moreover, then if phi is unital and PPT, then they managed to show that the its rays of or composition of phi with certain positive integer k then is separable. The conjecture, of course, is whether k equals 2, right? If k equals 2, then they solve the conjecture. But the trouble is that for the result, they don't know what is exactly the k. Okay, so now by making use of previous theorem, okay, and we can show that in the case n equals 2, so it means that from M3 to M3, then this conjecture is true. Okay? So it means that if phi is PPT, then the composition is separable. Now this result and many more important results then is proven also by the Christian and Ernest and Wu. They have a lot of very substantial results, okay, other than just this the result for this conjecture. Now apparently the conjecture for n bigger than or equal to 4 is still open. Okay, and then I think a lot of people would think that the conjecture will be false when n equals 4, but so far there's no concrete counter examples. Okay, so I think I better stop here. Thank you for your attention. Yeah.